Swayam Prabha. Digital India. Educated India.
The presenter is Xiu Qi Lian in the virtual. Do you hear me?
Yes.
Okay, so could you show your slide? Okay, now. Yeah, okay. So the title is shown here, the design of heat integration and systems for batch processes. So if you're ready, please start the presentation.
Okay. Thanks, moderator. Ladies and gentlemen, thank you all for being here. My name is Xiuqi Liang. I am graduate student at Department of Chemical and Material Engineering in Tonghai University. Today, I am going to speaking about study of design of heat integration system for batch process. Here is my outline. This presentation is divided 5 parts. Next, I am going to start with introduction and motivation. Okay. According to the global goals for sustainable development, it hopes to facilitate access to energy research and technology in order to increase energy efficiency. Carbon dioxide reduction also an important issue. Many countries are valuing net zero. In order to achieve the goal of net zero, we study on heat integration for batch process to decrease energy consumption. In the past, heat integration for batch process has been largely neglected because batch process are time-dependent process. It costs to the intrinsic time concentrates, and the batch process in general is energy intensive than continuous system, but still increase energy cost and enhance focus on emission reduction in recent years have changed this attitude among engineers and researchers. So we need novel heat integration strategies. For this design, given a hot and cold process stream in certain time interval to determine the objective minima cold and hot utilities. For heat integration of batch process, we have 3 strategies. First, heat integration in each individual time interval. Second, heat integration across time interval. Finally, heat integration in batch process scheduling. Okay. We use multi-period transfer model to do heat integration for batch process. Multi-period transfer model is different to traditional transfer model. It considers time factor P. Then we can achieve the goal of first strategy. This model could estimate heat integration in each individual time interval. QHIKP and QCJKP are heat content of hot stream and cold stream in interval K in P. QIJKP is exchange of heat of hot stream and cold stream at interval K in P. QINKP is exchange of heat of hot stream and cold utility at interval K in P. QSMP and QWMP are heat load of high utility and cold utility in P. Q and JKP is exchange of heat of high utility and cold stream at interval K in P. RIKP and RNKP are heat reducer of high stream and high utility extend interval K in P. We do the energy balance for multi-period transfer model to find out the objective of minimal hot and cold utilities. Next, we go into multi-period transfer model, consider heat transfer to across time interval. Here is model heat transfer across time interval. We add two variables, QR in IKP and QR out IKP on multi-period transfer model. Then model consider heat in less time could transfer to this interval, and the heat in this time interval could transfer to next interval. Here is a multi-period transfer model formulation. First formula is energy balance in this point. Second is energy balance in this point. Third, also energy balance in this point. Fourth is energy balance in this point. Next, I am going to model formulation consider heat transfer to across time interval. This is multi-period transfer model formulation heat transfer across time interval. Just need to modify hot stream balance formula. Added two variables QR out IKP and QR in IKP, and we need to add new concentrations QR out IKP equal to QR in IKP prime. P prime equal to P plus 1. Then heat can transfer to next interval. Third, fourth, and fifth formula are sent to basic multi-period transfer model. This is models objective function to minimize utility cost. C is utility price, Q is utility demands. Now, I am going to move to case study. Case 1, heat integration for batch process. Case 1, stream data have 4 hot stream and 3 cold stream, and provide inlet temperature, target temperature, and operation time. Then we could do heat integration. This figure is case 1 process stream Gantt chart. This figure could find out operation time of hot and cold stream, and this case divided time into 5 periods. Case 1 consider 2 scenarios. Scenario 1, heat integration in each individual time interval. Scenario 2, heat integration across time interval. This figure indicates the result of heat integration in each individual time interval. After heat integration, we can see our utility demand reduced to 228.6 kilowatt. core utility demand reduced to 110 kilowatt. Senior. This figure indicates the result of heat ingression across time interval. Due to heat ingression of scenario 2 across time interval, the result of heat integration should better than scenario 1. So we could see period 2 could provide heat to period 3. So high utility demand reduced to 192.2 kilowatt, and core utility demand reduced to 73.6 kilowatt. Case 1 summary. Multi-period transfer model was successfully developed for batch process. First is heat ingression in each individual time interval. Second is heat integration across time interval. With the result of scenario 1, hot and cold utilities can be reduced by 52 and 69%. With the result of scenario 2, hot and cold utilities can be reduced by 60 and 79%. Okay. Now we go into case 2. Case 2, heat integration in batch process scheduling. Case 2, given a batch process flowchart in form of STN, we have 5 tasks and 2 products. Here is essential process data for case 2 scheduling and heat integration, capacity, task, and utilities. We could see E2 and E3 suitable for task 2, 3, and 4. So we need to scheduling to find the mass product. Case 2 consider 2 scenarios. Scenario 1, sequential design strategy. Sequential design means scheduling for batch process to achieve mass product, then use the result of scheduling to do heat integration. Scenario 2 is simultaneous design strategies. Okay. The figure indicates the result of sequential scheduling. We could find out the operation time of all tasks, and this process divided into 10 periods. In this optimal schedule, we have product 1, 136 kilogram, product 2, 114 kilogram. We use the result of sequential scheduling to do heat integration. Then we could obtain high utility demand is 27,150 kilowatt. Cold utility demand is 26,801 kilowatt. This figure indicates the result of simultaneous scheduling. We have the same result of product 1 and product 2, but we could find out simultaneous scheduling is different to sequential scheduling, because simultaneous design consider more chance of heat exchange in scheduling. In scenario 1, T1 separate to period 2 and period 4. But in scenario 2, period 2's P1 combine period 4's P1 and arrange to period 1. So he can provide more chance of heat exchange. Simultaneous design consider more chance of heat exchange, so the result of heat integration should better than scenario 1. Due to T1 arranged to period 1. So period 2's heat period 2 could provide more heat to period 3. So power utility demand reduced to 25,370 kilowatt. Coal utility reduced to 24,336 kilowatt. Case to summary. Heat integration in batch process scheduling has been studied. First is sequential design. Second, simultaneous design. Then with simultaneous design strategies, more heat could be recovered by process rescheduling, and minimal utilities can be achieved. Conclusion. Heat integration system for batch process has been developed. First is multi-period transfer model with heat transfer across time interval. Second, heat integration in batch process in scheduling. And our case study show power and coal utilities are decreased significantly by the proposal approach. And with heat integration in individual time interval, heat transfer across time interval, and process scheduling, maximum heat recovery can be realized. That's all my presentation. Thanks for listening.
Thank you for the presentation. So now I take the questions, comments from the audience. Do you have any?
Hi, thanks. Just a quick question on the computation part. So I'm assuming that the second problem was more challenging to solve. Do you have any comparison of how much time it took to get the answer and whether it is truly optimum answer?
Did you clearly hear the questions? How long did you take? How long was it take to calculate to obtain the solution? That's the first question, right?
Yes.
How long is the calculation time of the second case study?
Yes. Sorry. Is
what was the computational time for the optimization?
Sorry, his voice is a little small. I can't hear.
How long was computational time? Okay, so let's please contact the email or something later. So then the time is coming, so let's thank again to the speaker. Okay, so now I would like to conclude this session. Thank you for coming and thank you for attending and thank you for the presenting. Everybody, I thank. And
Oh,
do you have
so-
any announcement?